Hey, welcome back to Valiant PE. Today's topic, stress, strain, elongation, Hooke's law. Let's go. All right, like normal, we're going to go through a problem, we're going to solve it, and then we're going to go back and take a look at what concepts make it a PE level question. So before we get started, every time we do a problem, pre-question ritual, come up with your own, anything to reset your brain before going into the next problem. That's the way to go. I like to read the problem slowly and write what I'm solving for. Here we go. Two parallel wires 7 inches apart, one of metal A and one of metal B, are used to support a load P. The area of wire A is 2.5 times the area of wire B. Determine the distance x from wire B for applying the load so that the wires will remain equal in length. We've got Young's modulus for wire A and B, 30 million and 10 million psi. We got some answer choices, and before we do anything else, I'm writing what I'm solving for, which is x in inches. Then let's look at our imagery, see what we've got here. We've got a bar and 2 wires. Any info given that's not, any info in the picture that's not given in the text, we've got this note here says infinitely stiff. I interpret that to mean that this bar, is not going to bend as a result of load P, that it's going to just stay rigid. I don't have to worry about bending effects. Okay. 2 methods to solve this problem. We're going to cover method 1, just one method today. First things first, we're going to start with setting our elongations equal to each other. Elongation in wire A is equal to elongation in wire B. Remember that our elongation formula, PL over AE. So I'm going to rewrite this guy, PAL over AA, EA is equal to PB, L, AB, EB. Can be a lot of letters in this problem. AA, remember that my area of wire A is equal to 2.5 times the area of wire B. So I'm going to rewrite this guy, PA, in terms of 2.5 AB, EA, PB, AB, EB. My L's up here cancel, so I should have said that. So now let's look at our image here and see if we can find anything specific about it. This looks to me like a simply supported beam with an off-center load. So we can go to our beam table and find that the reaction in wire A is equal to 1 minus K P, and reaction in wire B is Kp, where K is a ratio of the total length. So I'm going to rewrite my equation here now in terms of just P rather than PA or PB. 2.5 EA equals KP over EB. Also notice that my AB's cancel, so we're getting simpler every time. Now I'm going to rewrite in like terms on each side. EB over 2.5 EA is equal to K 1 minus K. Good, let's put some numbers to it. 30 million psi over 2.5 times 10 million psi. PSI's cancel, millions cancel. And I can solve for, there we go, 1 minus K. I can solve for that. 1.2 equals K over 1 minus K. Now, I'm going to come up here and I'm just going to do some algebra and solve for K. Got 1.2 times 1 minus K equals K. 1.2 minus 1.2K equals K. Just writing out in like terms. 2.2K, 1.2 over 2.2 equals K, which equals 0.545. Now, from our beam table, we can look and see that this distance, that is 1 minus K, and this distance, that's K. So this value looks an awful lot like this value, so let's set them equal to each other. X equals 1 minus K, which is a ratio of the entire length, L. Our length is 7 inches. 1 minus 0.545 times 7 inches. X equals 3.18 inches do we have that as an answer? Let's look at our answer choices. Bam, we do. Excellent. Okay, good. Now let's go see what makes this a PE level problem. Okay, beam table lookup. Beam tables can be your best friend if you know what you're doing with them, if you know what you're looking for. They are a little mysterious. Sometimes the images and what the info given next to the images can be confusing. For instance, simply supported beam with an off-center load gives you the image that you see in red here. Just this. You've got a distance KL, a load P, then you're given some info about R1 and R2. But R1 and R2 aren't labeled on the diagram. I mean, it may seem silly, it may seem simple, but it's not self-explanatory. You have to have used these beam tables enough to know that that's R1 and R2. My point here is that beam tables can really shorten the time required to solve a problem if you have used them enough to know what you're looking for, especially if you're going to look at like max deflection or max moment or max shear. They can be very confusing. So do enough repetitions where you can solve the problem using beam table only and be very confident with it. If you're going to try to do this in the middle of a problem, you're going to try to decipher some of the stuff given in these images here, it's going to be quick, or it's going to be difficult to solve. The second thing is sequential concepts. And this is pretty common with PE questions, is all the info needed to solve them in pieces is pretty simple. But stacked on top of one another becomes a lot more challenging. By reading the problem text, we ought to be able to understand that we can solve this problem using elongation. That's what we're getting at. But you have to be comfortable with setting things like elongation equal to each other and not really having a whole lot of numbers to put to it, and you're just working through and canceling. Once you do that, you can see that we've got a simply supported beam. So looking at the table, or excuse me, looking at the image, we can find we've got a simply supported beam, and then we can go straight into our beam table to solve the problem. So each of these concepts on their own are fairly straightforward, but if you get one of them wrong, all those that follow are going to be wrong as well. So my suggestion here is practice all of these guides individually, be comfortable with them so that you can easily stack them on top of one another in the middle of a problem and do it in 6 minutes. So the key here is repetition, confidence with the puzzle pieces, with the building blocks, and then you can put the building blocks together quickly in the middle of a problem. So let's go back and see, where are these concepts hiding? Okay, here's our elongation. Right up front, we've got the elongation formula and setting elongations equal to each other. And then we've got the beam table hiding down here. Okay, that's this guy right here. Now, let's quickly look at our last little bit here. Notice that the K and the 1 minus K that I wrote here are the same as what I just showed you down from the reference manual. So not a lot of complex info here, but put together can be a tricky problem. So remember, guys, you don't have to be a genius to solve, or you don't have to be a genius to pass this exam. See you next time.